Okay, in today's lecture, we're going to cover the section 4.7 material on change of basis. So we know that when we assign a basis, let's call it B, to an n-dimensional vector space, V, then the associated coordinate mapping from V onto Rn provides a coordinate system for that vector space V. Now, for each vector x in our vector space V, we can identify a unique B coordinate vector, which we would call the coordinate vector of x relative to the basis B. But in some applications, a particular problem involving a vector space might be described initially using a basis B. However, the basis that we're initially given might be a little bit complicated. So the solution to this problem could be aided by changing the basis B to a new simpler basis C, in which case each vector is assigned a new C coordinate vector. So in this section, we're going to consider how the coordinate vector for a vector x relative to the basis B is related to the coordinate vector of x relative to the new basis C. So as an example, let's consider the following problem. Suppose that we have a basis B consisting of vectors B1 and B2, and a basis C consisting of vectors C1 and C2 for some vector space V. And we know how the vectors B1 and B2 are related to C1 and C2 by the given equations. And we have a vector x, which is described in terms of the basis vectors B. X is 1b1 plus 3b2. And we want to then find the coordinate vector for x relative to the new basis C. So let's take a look at how this would work. We know that since the coordinate mapping is a linear transformation, if we're interested in finding the coordinate vector of x relative to the basis C, then that is the same as the coordinate vector of B1 plus 3b2 relative to the basis C, since x was given as the sum of b1 plus 3b2. So since this coordinate mapping is a linear transformation, this is the same as the coordinate vector of b1 relative to C plus 3 times the coordinate vector of b2 relative to C. Now we could express this vector equation in terms of a matrix equation. So let's say writing this as a matrix equation. We could have the coordinate vector of x relative to the basis C is given by the product of the matrix whose columns are the coordinate vectors of B1 and B2 relative to the basis C. And then we're multiplying by the vector of weights for those coordinate vectors, which were 1 and 3 here. So once I know what these two column vectors are for this matrix, I can take this product and I've got my coordinate vector. Now in this example, we can find the coordinate vectors for B1 with respect to C or B2 with respect to C directly from the problem statement. So we were told here that B1 is equal to C1 plus 4C2. So by definition, the coordinate vector of B1 with respect to the basis C would be the vector of these coefficients, 1 and 4. And the coordinate vector of B2 relative to the basis C, well, looking at our equation for B2 in terms of the basis vectors for C, we had 1C1 minus 6C2. So our coordinate vector would be 1, negative 6. So we now have the coordinate vector of x relative to the basis C is equal to the matrix which has these two vectors as its columns. So that is 1, 4, 1, negative 6 times our vector 1, 3 that we had seen from this previous line. So taking this product, we have a 2 by 1 vector whose first entry is 1 plus 3 or 4, and our second entry would be 4 minus 18, so negative 14. So this would be the coordinate vector of x relative to C. So recall what this is telling us is that the vector x can be expressed in terms of the basis vectors for the basis C as 4 times C1 minus 14 times C2. All right. So the matrix which we're considering in this example, that is this matrix which takes my vector x that we're given, or the coordinate vector for x relative to the basis B, and transforms it into the coordinate vector of x relative to the basis C, will be given a special name. So the argument which we used in this first example, or this procedure, can be generalized to achieve the following result, known as theorem 4.15 in your textbook, which says if we have a basis B consisting of n vectors and a basis C consisting of n vectors, which are bases for a vector space V, then there exists a unique square matrix, which is denoted as P with a subscript B moving to C, or from B to C, such that the coordinate vector of x relative to the basis C is given by a matrix, that matrix P with the subscript from B to C, times the coordinate vector of x relative to the basis B. Now, as we saw in our first example, the columns of this matrix are the C coordinate vectors of the vectors in the basis B. So that is, this matrix that we're interested in is the matrix whose column vectors are the coordinate vectors of the basis vectors that we're moving from, that is from basis B, relative to the new basis C. So this matrix that we're making use of here is called the change of coordinates matrix from the basis B to the basis C. And as we've seen in our first example and in this theorem, multiplication by this matrix converts the B coordinates into C coordinates. So we can visualize this change of coordinates matrix along with our coordinate mappings as follows. So let's suppose that we have some vector space V, which consists of some vectors. Let's choose one of them and call it X. So if we assign a basis to this vector space V, let's say a basis B, we have a coordinate mapping from our vector space, the coordinate mapping assigned by the basis B, which gives us an n-dimensional vector, since there were n vectors in our basis. And the vector that we're assigning would be the coordinate vector of x relative to this basis B. Now, if we choose a different basis for our vector space V, we have a different coordinate mapping assigned by the basis C, which would, again, give us some vector in our n, since we had n as the dimension of our vector space V. And we would have a coordinate vector of x relative to the basis C. So if I'm interested in transitioning from Rn to Rn and just making a change of coordinates, well, we could take the coordinate vector of x relative to b and multiply by this change of coordinates matrix, which is denoted as capital P with a subscript moving from B to C. Now, if we're interested in moving in the opposite direction, that is from the basis C to B, let's think about how we could do it. Now we know here that the columns of this change of coordinate matrix are linearly independent because they are the coordinate vectors of the linearly independent set B. So these columns were coordinate vectors for basis vectors, which are by definition linearly independent. So this coordinate mapping preserves that linear independence of those vectors. Now, since this matrix is a square matrix, we have a square matrix whose columns are linearly independent, and therefore this matrix must be invertible, as guaranteed by the invertible matrix theorem. So this matrix has an inverse, and if we consider left multiplication of the equation from theorem 4.15 by the inverse of this matrix, so we're taking the equation shown in theorem 4.15 right here, and if we were to left multiply both sides of that equation by this inverse matrix, we would have the product of the inverse matrix of the change of coordinate matrix from B to C times the C coordinate vector for x. We would get the coordinate vector of x relative to B. So we can consider this inverse matrix as the matrix that is converting C coordinates into B coordinates. So that is this inverse matrix from B to C is the same as the change of coordinate matrix from C to B. So since we know this is invertible, we could move in the opposite direction by multiplying a coordinate vector of x relative to the basis C by the change of basis matrix from C to B, which is the same as the inverse of the change of coordinate matrix from B to C. All right. So let's look at some special cases for this change of coordinate matrix, and then look at some examples of how to find this matrix and how it can be applied. So the next thing that we'll talk about is a change of basis in Rn. So in the case that we have a set of basis vectors, b1 through bn for Rn, and E is the standard basis consisting of the vectors e1 through en, so those are the columns of the n by n identity matrix for our vector space Rn. Then the coordinate vector of b1 relative to the standard basis, E, would just be b1 itself. and similar for the other vectors in the basis B. So in this case, the change of coordinate matrix from B to E would be the same as the change of coordinates matrix P sub B that we had introduced in section 4.4. So recall that that change of coordinates matrix P sub B was the matrix which has the basis vectors as its columns. So if we're interested in changing coordinates between non-standard bases in Rn, then we have to make use of theorem 4.5. If one of our bases is the standard basis, then we can make a change of coordinates just using the change of coordinates matrix that we saw in earlier sections. But if we're using two non-standard bases, then we have to make use of this new theorem. So let's look at an example of this. So suppose that we have two bases, B and C, consisting of two vectors, B1, B2, and C1, C2, for some vector space V. And let's suppose that B1 and B2 can be expressed in terms of the basis vectors C1 and C2. So we are, in part A, supposed to find the change of coordinates matrix from the basis B to the basis C. So recall by definition this change of coordinate matrix from B to C is the matrix whose columns are the coordinate vectors for our basis vectors, B1 and B2, relative to the basis C. So to get our matrix, we're going to take the matrix whose columns are these coordinate vectors. And we can get the coordinate vectors for B1 and B2 relative to the basis C directly from the problem statement. So we were told, for instance, B1 is negative C1 plus 4C2. So this first column of our change of basis matrix will be the coordinate vector negative 1, positive 4. And we were told that B2 is equal to 5C1 minus 3C2. So those weights for the vector C1 and C2 give us this second column, 5, negative 3. So this would be our desired change of coordinates matrix. Now, to apply this change of coordinates matrix, let's suppose that we have a vector x in our vector space, which can be expressed in terms of the basis vectors for B. And we want to find the coordinate vector for that vector x relative to the basis C. So here, we could start by saying the coordinate vector of x relative to the basis B is given by 5, 3, since x was 5b1 plus 3 times b2. That would be our coordinate vector. And so, by theorem 4.15, we know that the coordinate vector of x relative to C can be found by taking the change of coordinates matrix from B to C and multiplying by the coordinate vector of x relative to B. So let's see what we have here. We would have our matrix from part A, which was negative 1, 5, 4, negative 3. And we're multiplying by our coordinate vector 5, 3. So we get the 2 by 1 vector. Here we have negative 5 plus 15, so 10. And for our second entry, we would have 20 minus 9, which is 11. So that, again, means that the vector x could be expressed as 10c1 plus 11c2. All right. So let's look at another example, maybe working with a higher dimensional vector space. So in this next example, we have a set of vectors a1, a2, a3, and b1, b2, b3, which are bases for some vector space V. And let's suppose that a1 and a2 and a3 can all be expressed in terms of these basis vectors b1, b2, and b3. So in part A, we are again asked to find the change of coordinates matrix from A to B. So as with our last example, let's think about the definition of this change of coordinates matrix from A to B. So by definition, it is the matrix whose column vectors are the coordinate vectors of the basis that we're moving from. So those are the vectors a1, a2, and a3 relative to the new basis B. So these columns for our matrix, which are these coordinate vectors, can be found directly from the problem statement, since we knew how to express a1, a2, and a3 in terms of the basis vectors b1, b2, and b3. So our first column, the coordinate vector of a1 relative to b, would have entries 2, -1, +1. Since a1 was 2b1 minus b2 plus 1b3. Now our second column would be 0, 3, 1, since a2 was equal to 3b2 plus 1b3, and we didn't have any a1 term appearing, or b1 term appearing there. And then our third column, the coordinate vector of a3 relative to b, is given by -3, 0, 2. Since our third vector a3 was -3b1 plus 0b2 plus 2b3. So this is our change of coordinates matrix. And now for any vector x that is written in terms of the basis vectors A, we can now convert to the expression for x in terms of the basis vectors B. So here we're asked to find the coordinate vector of x relative to B if x is a1 minus 2a2 plus 2a3. So our first step here would be to find the coordinate vector of x relative to the basis A, which here is given by 1, -2, +2, since x was given in terms of those vectors. So to find the coordinate vector of x relative to B, we take the product of our change of coordinates matrix from A to B times the coordinate vector of x relative to A. So using our matrix from part A, we have the matrix 2, 0, -3, -1, 3, 0, and 1, 1, 2. And we're multiplying by the vector 1, -2, +2. So this product results in a 3-by-1 vector, where our first entry would be 2 plus 0 minus 6, so -4. Our second entry is -1 minus 6 plus 0, so -7. And our third entry would be 1 minus 2 plus 4, which leaves us with 3. So again, this implies that the vector x could be written as -4 times b1 minus 7 times b2 plus 3 times b3. All right. So a couple of examples illustrating how to find this change of coordinates matrix from one basis to another, and how it can be used in order to find a coordinate vector of x relative to a given basis if we know the coordinate vector relative to one basis already. Now, in these first few examples that we've been considering, some of our basis vectors, for instance, in this example, the basis vectors a1, a2, and a3, we were given the expression for those three basis vectors in terms of the other three basis vectors, b1, b2, and b3. But in most examples, we do not immediately know how to express one basis vector as a linear combination of other basis vectors. So let's consider an example that would appear more frequently in applications, where we're given two sets of bases and we know what the basis vectors are, but maybe we don't want to, or we aren't able to find an expression for the basis vectors for one basis as a linear combination of the basis vectors for the other basis. So as an example of such a problem, suppose that we have two bases, B and C, which are bases for R2, so they consist of two vectors each. And we know what the values of these vectors are. B1 and B2, C1 and C2 are both given. And here we want to find the change of coordinates matrix from one basis to the other, say from B to C. Now we know that by definition, the change of coordinate matrix P from the basis B to C is the matrix whose columns are the coordinate vectors of B1 and B2 relative to C. So if we need to find our matrix, we need to know what those column vectors are, what the coordinate vectors are. And here we can't read them directly from the problem statement. So let's set up an equation to find those coordinate vectors. Let's say the coordinate vector of B1 relative to C is a vector, let's call it x1, x2. Has to be two-dimensional since we're considering a basis for R2. And the coordinate vector for B2 relative to C will be the vector, let's call it y1, y2. Then, by definition, we know that x1 times c1 plus x2 times c2 has to equal b1, and y1 times c1 plus y2 times c2 has to equal b2. This is the definition of a coordinate vector. So if we were to express this in matrix form, we could write this as a matrix whose columns are C1 and C2 times the coordinate vector x1, x2, which would have to equal the vector b1, and the matrix whose columns are C1 and C2 times this vector of weights, y1, y2, is equal to b2. So we need to solve these two systems of equations for x1, x2, and y1 and y2. But rather than solve these two systems separately, to save ourselves a little bit of work, we could consider taking the coefficient matrix, which is the same for both systems, the matrix whose columns are C1 and C2, and augment rather than with a single vector, b1 and b2 individually, we could augment that coefficient matrix with both of these vectors, b1 and b2, and solve both systems simultaneously. So let us consider augmenting the coefficient matrix with both vectors b1 and b2. So that is, we would have our coefficient matrix whose columns are C1 and C2, so 1, 4, and 1, 1, since C1 and C2 were given in the problem statement. And then we're augmenting that with the matrix whose columns are B1 and B2, which were -1, 8, and 1, -5. So now we want to row reduce this matrix in order to solve our system. So that is, we want to transform the matrix on the left-hand side of this augmented matrix into the identity. So we could start by taking row 2 and subtracting 4 times row 1. So our first row will be 1, 1, and that makes our second row 0, -3. So I'm doing the same operation to the matrix on our right-hand side, while our first row is left alone, -1, 1. And the second row becomes, let's see, we would have 4 plus 8 is 12, and then -4 minus 5 is -9. So now, in my second row, I could, in order to get a leading entry of 1, divide everything through by -3. So that is, take -1/3 of the second row. So our first row will remain 1, 1. The second row becomes 0, 1. In performing the same operation on the matrix on the right-hand side, our first row remains -1, 1, and dividing the second row by -3, we have -4 and +3. So in our last step, to eliminate the 1 in that top right entry, we could take row 1 and subtract row 2. Which gives us the identity matrix 1, 0, 0, 1, augmented with the matrix 3, -2, and -4, 3. So this matrix which we have on our right-hand side has columns which are the desired coordinate vectors for b1 and b2 relative to C. Those are the values of x1, x2, and y1, y2. So here, our coordinate vector for b1 relative to C would be the vector 3, -4, and the coordinate vector for b2 relative to C would be the vector -2, 3. So taking those coordinate vectors and placing them in the columns of a matrix, we have the desired change of coordinates matrix. So we can say our change of coordinate matrix from B to C would be the matrix whose first column is 3, -4, and our second column is -2, 3. All right. Now one thing to notice here is that change of coordinates matrix was the exact matrix that we had here. After we took the augmented matrix whose columns were C1 and C2, augmented with the matrix whose columns were B1 and B2, and we row reduced this left-hand side to the identity matrix. So here this is exactly the matrix that we were after. So this process can be generalized, and we see that the first column we see that the matrix, change of basis matrix, P from B to C, was obtained by row reducing the first column of that matrix was obtained by row reducing the matrix C1, C2 augmented with B1 to the identity matrix, where we were augmenting with the coordinate vector of B1 relative to the basis C. And we had a similar result for the second column of that change of coefficient matrix, or change of coordinate matrix. So in general, we could take the augmented matrix where we have on the left-hand side the basis vectors with respect to the new basis that we're after, C, augment with a matrix whose columns are the basis vectors for the old basis, B, and then row reduce that such that the left-hand side becomes the identity matrix and the right-hand side will be our change of coordinates matrix. So, of course, we have a similar procedure which would work to find the change of coordinates matrix between any two bases in Rn. So let's consider another example of this problem, but where we can make use of this augmented matrix to simplify our work a little bit. So in this next one, we have two bases, B and C, for R2, each consisting of two vectors, and we want the change of coordinates matrix from B to C, and the change of coordinates matrix in the opposite direction from C to B. So we know to get the change of coordinates matrix from B to C, we could consider the augmented matrix, where our columns on the left-hand side are C1 and C2. That is 4, 1, and 5, 2. And we would augment with the matrix whose columns are the basis vectors B1, which was 7, negative 2, and B2, that is 2, negative 1. And then we would row reduce our matrix on the left-hand side to the identity matrix. So to start here, we could take the matrix that we get by interchanging rows 1 and 2. I know I want my top left entry to be a 1. An easy way to get that here would be to just interchange my first two rows. So by interchanging row 1 and row 2, our first row becomes 1, 2. Second row is then 4, 5. And interchanging the two rows on our right-hand side, we have negative 2, negative 1, and 7, 2. So now I have the leading entry of 1 in the first row that I wanted, which I can use to eliminate the 4 that appears as the lead entry in my second row by taking row 2 and subtracting 4 times row 1. So our first row will remain 1, 2, and our second row we have 0, and then negative 8 plus 5 would be negative 3. Augmenting with, first row stays negative 2, negative 1, and performing the same operation on the right-hand side, we would have 8 plus 7 is 15, and then 4 plus 2 is 6. So now, to change the lead entry in our second row from a negative 3 to a positive 1, well, we see everything in that second row is divisible by 3. So we could take a negative 1/3 of the second row. So our first row will remain the same, 1, 2, and negative 2, negative 1. In our second row, dividing through by negative 3 becomes 0, 1, and negative 5, negative 2. So now my leading entry in the second row is a 1, which I can use to eliminate the 2 that appears above it by taking row 1 and subtracting twice row 2. So this gives me a first row of 1, 0. The second row is still 0, 1. So the second row on the right-hand side is still -5, -2. And performing this operation on the right-hand side, we have 10 minus 2 is 8, and 4 minus 1 is 3. So this matrix on our right-hand side is the change of coordinates matrix that we're after. That is the change of coordinate matrix from B to C. Is 8, 3, -5, -2. Now, if we want in addition, the change of coordinate matrix from C to B, we need to find the inverse of this matrix. Recall, the inverse of a change of coordinate matrix is the change of coordinate matrix acting in the opposite direction. So for the inverse of a 2 by 2, we need to find the determinant of this matrix, which here would be -16 minus a -15 would give us +15. So we have a determinant of -1. And so using our formula for the inverse of a 2 by 2 matrix, we can get the change of coordinate matrix from C to B as the inverse of the matrix from B to C. By taking 1 over the determinant, so 1 divided by -1 gives us -1, and then we multiply by the matrix we get by interchanging the diagonal entries of our original matrix. So we have -2 and 8 as our diagonals, and we take the off diagonals and make them, or take the negative of those values, so -3 and +5. So then distributing our -1 out in front, we have 2, 3, -5, -8. All right. So these were the two matrices that we were interested in, the change from B to C, and what we've just found was the change from C to B. All right. Now in our last example, let's consider a vector space involving something other than Rn. So perhaps a space of polynomials, say for instance in P2, the vector space of polynomials degree 2 or less. We want to find the change of coordinates matrix from the basis B, given by 1 minus 3t squared, 2 plus t minus 5t squared, and 1 plus 2t, to the standard basis E, which is 1t squared. And then using that matrix, we want to write t squared as a linear combination of the basis polynomials for B. So again, if we think about the definition of the change of coordinate matrix from B to the standard basis E, it is the matrix whose columns would be the coordinate vectors of the basis vectors that we're moving from relative to the new basis. So that is the coordinate vectors of B1, B2, and B3 relative to the standard basis E. Where B1, B2, and B3 are the three polynomials given in the basis B. All right, so let's see if we can find those coordinate vectors. Since we're moving directly to the standard basis, we can see by inspection of the polynomials in the basis B what the coordinate vectors are. So the coordinate vector for our first polynomial, B1, relative to the standard basis, well, we have 1 as our constant. So 1 for the coefficient of t to the first, we had 0. And for our coefficient of t squared, we had -3. Now for our second column, we would look for the coefficients of B2, that is the second polynomial, relative to the standard basis vectors, 1, t, and t squared. So here we have a constant of 2, a coefficient of t being 1, and a coefficient of t squared as -5. And then for our third basis polynomial B3, which was 1 plus 2t, we have a coefficient vector relative to the standard basis of 1, 2, and 0. All right. So we found the first part of the problem, the change of basis matrix from B to E. So now we're supposed to take the polynomial that we're given, I'm going to call it P of t, which is t squared, and write it as a linear combination of the polynomials in the basis B. So what we're looking for is the coefficient vector for this polynomial relative to the basis B, which we could find by taking the change of basis matrix from the basis E to the basis B, and then multiply by the coefficient vector of P relative to the standard basis, which is known. However, what we found in the first part of this problem was the change of coordinate matrix from B to E, and we need the opposite direction from E to B, which would be the inverse of the matrix which we just found. So we would take the inverse of our change of coordinate matrix from B to E, and then multiply by this coordinate vector of P relative to the standard basis. Now, that would involve finding the inverse of this 3 by 3 matrix, which we could do either making use of that adjoint expression from chapter 3 or by augmenting this matrix with the 3 by 3 identity matrix and then row reducing. And then we would have to multiply the 3 by 3 inverse matrix by our coordinate vector shown here. So this is one approach that we could use, but we see that this starts to take a little bit of work to find that inverse matrix. So an alternative approach would be to make use of what we had seen in our previous chapter 4 material. So I'll say alternatively, we could consider letting a linear combination of our basis polynomials, let's say C1 times the first polynomial in our basis B, which was 1 minus 3t squared, plus C2 times 2 plus t minus 5t squared, plus C3 times 1 plus 2t, equal to the given polynomial t squared, and then solve for our coefficients C1, C2, and C3. So expanding and grouping like terms, we have a constant coefficient of 1c1 plus 2c2 plus c3, plus we have a coefficient of t of c2 plus 2 times c3, and a coefficient of t squared of negative 3c1 minus 5c2. And that has to equal t squared. So in order for these functions to equal each other, the coefficients have to match. So we have the sum of c1, 2c2, and c3 is 0. c2 plus 2c3 is 0. And then our coefficient for t squared, negative 3c1 minus 5c2, has to equal 1. So setting up that system of equations as an augmented matrix, we have the matrix 1, 2, 1, 0, 1, 2, and negative 3, negative 5, 0. That is the same matrix that we found above. And we're augmenting with our vector 0, 0, 1, the coefficients that we had for our polynomial t squared. So now solving this system through row reduction, we can show that this matrix is row equivalent to the following: 1, 0, 0, 0, 1, 0, and 0, 0, 1, augmented with 3, negative 2, 1. So this implies that t squared can be written as 3 times the first of our basis vectors, which was 1 minus 3t squared, minus 2 times the second basis vector, which was 2 plus t minus 5t squared, plus 1 times our third basis vector, which was 1 plus 2t. And you can verify that that is indeed true. If you expand this expression, you'll see that you get simply t squared. So in this section, we've seen how to convert from a coordinate system implied by one basis to a coordinate system implied by another basis. So it involves finding this change of coordinates matrix, which relies on us augmenting or forming an augmented matrix whose columns are the basis vectors for one of our bases, and where the other matrix within our augmented matrix has columns whose are column vectors, which are the basis vectors for our other basis in performing a row reduction on that given system. And if we have a change of coordinate matrix from one basis to the other, we can find the change of coordinate matrix in the opposite direction by finding the inverse of the given change of coordinate